Last time we ended with a set that survives its own two operations. Two vectors and out falls the plane. Here's V again. 3 along, 2 down, the same vector since episode 1. Look at what the rules of a vector space say. The 0 vector is in there. Add 2 vectors and you stay inside. Scale 1 and you stay inside. That's the whole test. Read it again and notice what's missing. No ruler. No protractor. Nothing mentions how long anything is, or what angle 2 arrows make. Which seems like an oversight, because the length is right there. The arrow has a length the way a stick does, a physical fact, waiting to be measured. Coordinates just record it. 3 across, 2 down, you've written down something that already had a size. That belief is reasonable. Every arrow you've drawn came out of a pen with a length of its own. In the 1840s, Hamilton was working on a system where multiplying 2 directed quantities handed you back a number and a direction at once. That number part is one ancestor of what's here. Grassmann reached his own version of it independently. If nothing in the rules measures anything, where does an arrow's length come from? Take 2 vectors u and v, both with n real components. There's an operation with nothing to do with pictures. Multiply the first component of u by the first of v. Multiply the second by the second, keep going, and add everything up. That's the inner product of u and v. u1 v1 plus u2 v2 to un vn. Our u is 1, 2. Our v is 3 minus 2. Same vectors, new operation. 1 times 3 is 3. 2 times minus 2 gives minus 4. 3 plus minus 4 is minus 1. The inner product of u and v is minus 1. Look at what came out. Not an arrow. Not a pair. A single negative number. 2 vectors went in, and 1 plain scalar came out. Nothing in that definition looked at a picture or asked which way anything pointed. It multiplied numbers and added them, the only thing this subject has ever done. So far, it's a machine that eats 2 vectors and spits out a number. No reason yet to think it means anything. That number came from multiplying and adding. What if you feed a vector to itself? Forget the algebra and look at v on the plane. Drop a horizontal leg of length 3 and a vertical leg of length 2. A right triangle, and v is its hypotenuse. Pythagoras, 2,500 years old. 9 plus 4, the hypotenuse squared is 13. Now take the inner product of v with itself. 3 times 3 is 9, minus 2 times minus 2 is 4. 13. The same number, reached without drawing a single triangle. So we define it that way round. The norm, or length, of v is the non-negative number you get by taking the square root of the inner product of v with itself. For our v, that's the square root of 13, a little over 3.5. That square root is always available. The inner product of a vector with itself is never negative, and 0 only for the 0 vector. The word norm is doing real work. On abstract spaces, you can define an inner product whose norm has nothing to do with length. Grassmann's rules never needed a picture to begin with, and this one doesn't either. If length is defined so Pythagoras comes out true, what's a vector of length exactly 1, and how do you make 1? A vector u is a unit vector, if and only if its length is 1. Our u, 1 and 2, fails. Its inner product with itself is 1 plus 4, so its length is the square root of 5. About 2.2, too long by a factor of root 5. Divide by exactly that. 1 over root 5 and 2 over root 5. Check it. A fifth plus 4/5 is 1, and the square root of 1 is 1. A unit vector. It points exactly where you pointed, same direction, magnitude scrubbed off. The rule is general. For any v that isn't the 0 vector, v divided by its own norm is a unit vector in the same direction as v. That's normalizing v. Draw every unit vector at once, and you get a circle of radius 1. Every vector with components cosine theta and sine theta lands on that circle, one for each angle. Direction has come apart from length. Separate things, and you can hold one without the other. So can this number tell you how much of one direction sits inside another? Take the inner product of u and v and divide by both their lengths. What you get is the cosine of the angle between them. Rearrange and you get the projection of u onto v. The inner product of u and v over the inner product of v with itself times v. The shadow u casts on the line through v. Our numbers. The inner product of u and v was -1, and of v with itself 13. So the projection is -1/13 of v, a stub pointing backwards. Backwards because of that minus sign. The angle between u and v is more than 90 degrees, and the inner product says so. Under 90 degrees, it's positive. At exactly 90, the cosine is 0, so the whole thing is 0. Two vectors u and v are orthogonal, perpendicular, if and only if their inner product is 0. Nobody measured an angle. Perpendicularity is now an equation. Here's a new vector, s. Its components are 2 and 3. Inner product of s and v. 2 times 3 is 6, 3 times -2 is -6, 6 minus 6 is 0. Orthogonal, and the picture agrees, those arrows meet at a right angle. So what about the 0 vector? The 0 vector's inner product with v is 0. Every component is 0, so every product is 2. So the 0 vector is orthogonal to every vector there is, a point, perpendicular to everything. Absurd in a picture. The operation obeys rules, and they're the ones you'd hope for. Order doesn't matter. The inner product of u and v equals that of v and u. Check that on ours. 3 times 1 is 3, -2 times 2 is -4. -1 as before. It splits over sums, so the inner product of u plus v with w is the two inner products added. Pull a scalar c out of either slot, and it comes out front. The inner product of v with itself is never negative, and 0 exactly when v is the 0 vector. Those two made the square root safe. Then the last one. The norm of u plus v squared equals the norm of u squared, plus the norm of v squared, plus twice the inner product of u and v. Make u and v orthogonal, and that middle term is 0. The squares add. That's Pythagoras. Not for a triangle on a page, for vectors with 100 components where no triangle can be drawn. Every geometric fact here came out of multiplying components and adding. Not one proof looked at an arrow, which is why they survived the trip upward. Arithmetic doesn't care how many dimensions you hand it. Length and angle were never properties the plane had lying around. They're what one number, built out of multiplying and adding coordinates, decides they are, and that's why they follow you into spaces nobody can draw.